emergence describes how new, higher-level properties, patterns, and functions form as we put the component parts of a system together. This process of emergence is a pervasive phenomenon in our world, exhibited by virtually all types of complex entities, such as plants, animals, technology, humans, societies, cultures, and economies. It is apparent that new levels of organization are formed as we put things together. For example, when we look at a flower, we do not see a composition of molecules, cells, tissues, and organs, but in fact we see a whole flower. Likewise, a whole business organization is given characteristics and legal rights that are not associated with any of its members. Although this emergence of patterns on different levels is apparent, what is not so apparent is whether these emergent organizations are fully determined and understandable with reference to their basic component parts, or do they exist in some way independently from the elements that constitute them, which would mean that they cannot be entirely reduced to causal accounts derived from their elementary parts alone. This distinction in emergence is captured in the terms strong and weak emergence, where weak emergence refers to the idea that even though emergent phenomena are unexpected given the principles governing the lower level domain, they are still, however, fully explicable only with reference to the lower level phenomena. In contrast, a higher level phenomena is strongly emergent when it arises from the lower level domain, but the facts concerning the emergent phenomena are not derivable even in theory from the features of the lower level domain. Weak emergence is the phenomena whereby new and unexpected patterns emerge due to the interaction between the parts. The sheer number of parts and the interactions make it extremely difficult to compute this higher-level phenomena based solely upon the elementary parts and their rules. However, from the weak emergent perspective, given sufficient computational capability, it would be possible to derive the higher-level phenomena, and thus there seemed to be, at least theoretically, a derivative or what we call an epiphenomena. New phenomena and patterns do emerge, but the reason we cannot predict them is that the number of interactions between the components of the system increases exponentially with the number of elements, and we typically do not have the computational capabilities to deal with such a dynamic. With this weak emergence, it is possible to compute the higher-level phenomena, but typically much easier just to look at it directly. Thus, this weak emergence can be understood as a kind of explanatory emergence. That is to say, the emergent features are ontologically and causally derived, but in practice they are explanatorily irreducible due to the computational complexity. New rules may appear to emerge at the different levels, but ultimately, if we had the computational capabilities, we would be able to understand all of the rules at the different levels with respect to lower level rules. Thus, if you had an extremely high level of computational capability, you would not need to focus on the higher level phenomena, but understand it instead from first principles. In such a case, one could look at it as caused by its purely discrete cellular parts. An often cited example of weak emergence are cellular autonomous computer programs like the game of life. The game of life is played on a grid of checkers where a cell can be either on or off. There are 4 simple rules as to whether a cell should be on or off, depending on the state of its immediate surrounding neighbor cells. These simple rules, when computed, can create very complex and subtle emergent patterns that appear to have their own internal structure, such as blinkers that are a group of cells blinking on and off, or gliders that seem to glide across the screen, all of which are emergent phenomena. These programs also exhibit sensitivity to initial conditions, and it is very difficult to predict what will emerge based on the initial conditions and ground rules. Although these programs can create emergent patterns, they are said to be weakly emergent because they are determined by the elementary rules, the starting state, and because there is no downward causation. The macro-level system does not change the micro-level rules. This weak emergence is characterized by the interaction between parts as the system evolves, leading to computational complexity and the appearance of something new emerging, what in fact is theoretically reducible to causal accounts of the elementary parts. One cannot, in any straightforward way, derive the higher level phenomena from the fundamental rules. Thus, compact representations, such as equations, do not tell us very much about what is going on, because we need to compute the interactions to produce the higher level phenomena. These weakly emergent higher level phenomena do not affect the lower levels. That is to say, there is only upward causation present. The macro level is determined by the micro level, but not vice versa. There is an asymmetrical flow of determinism. Macro level patterns are not doing anything over and above what the micro level elements are doing to affect the position and behavior of the elementary parts. An event is thought to be strongly emergent when the higher level phenomenon derives from the lower level events, but a complete description of the emergent pattern is not reducible even in principle to an account of the elementary parts and their interactions. Along with this irreducibility, downward causation is commonly cited as a second criteria for strong emergence. Strong emergence entails the idea that something truly new emerges at the different levels of organization that cannot, theoretically, be reduced to accounts of the elementary parts. The whole is something truly other than the parts. Thus it makes sense to talk about qualitatively different levels or dimensions to the system, as the rules that apply on one level become replaced, at least partially, by rules of a qualitatively different nature on another level. These higher level patterns can then exert downward causation on their constituent parts to affect their structure and functioning. Strong emergence describes the direct causal action of a higher level system upon its component parts. Qualities produced this way are irreducible to the system's constituent parts. One of the classical examples of strong emergence given is quantum entanglement. Quantum entanglement is a phenomena within quantum physics where two particles' spin states becomes entangled, meaning the state of one is entirely dependent on the state of another. It has been empirically proven that the combined entangled organization determines the spin direction of the parts. The two particles can be light years away from each other, but if the spin is changed on one, this will be immediately reflected in a change in the spin of the other. Thus, the combined organization is in some way affecting a downward cause on the parts. Another example from physics of strong emergence is water, whose features are apparently unpredictable, even given a molecular or quantum mechanical analysis to the properties of its constituent atoms. It would appear that no computational description of the system can exist, for such a simulation would itself constitute a reduction of the system to its component parts. The emergent phenomena, in this case, cannot be described with reference only to fundamental rules, but instead requires some form of macro-level rule. Likewise, human consciousness is another often cited example of strong emergence. Whereas with closed systems, the whole should be theoretically derived and caused by the parts. This, however, may not be the case with open systems. The parts form the whole, but then the system has to interact with its environment as an entire system, and not simply as a set of parts. This interaction with its environment requires that it perform functions and activities as a whole system. An example of this might be walking, which can only be achieved by the different legs being coordinated and interdependent. For the system to operate within the environment as a whole, it may have to exert a downward effect on the parts in order to coordinate them towards performing the macro-level processes that are required to interact and respond to the environment. For example, we can derive the internal workings of a truck from the basic laws of engineering and physics. But using these same elementary internal rules, we would never be able to derive why the truck is designed to drive on the left or right-hand side of the road. This phenomena is not a product of the internal logic of the truck's design or of the physical laws that govern its workings. It is instead a product of the system's interaction with other systems and some historical, political, and economic contingent within its environment, which may be seen to be exerting downward causation on the design of the truck. The biologist Peter Corning illustrates this when he writes, quote, "The debate about whether or not the whole can be predicted from the properties of the parts misses the point. Wholes produce unique combined effects, but many of these effects may be co-determined by the context and the interactions between the whole and its environment." This question of strong and weak emergence is of major relevance, as it goes a long way to defining whether we should focus our inquiry on the micro-level structure and rules that give rise to the high-level phenomena, as would be the case if we posit that the world is weakly emergent, or whether we should instead focus on the internal patterns of the emergent phenomena in their own right, as would follow naturally from assumptions of strong emergence. As such, the concepts of strong and weak emergence form part of the foundations within the different scientific paradigms of reductionism and holism. Reductionism is based on the premise that complex phenomena can be broken down into simple building blocks from which higher-level events can be reconstructed. Thus, a reductionist approach would typically ascribe to a weak emergent view of the world, where complex macro-level phenomena would admittedly take vast amounts of computation to derive from the basic physical building blocks, but however, given such a capability, they would be fully explicable from the elementary parts and rules. The weak emergent theory inspires the idea that the goal of science is to understand the basic building blocks and rules for their construction, and drives a quest for the theory of everything as seen to be found in some elementary parts, as is currently the quest of such approaches as string theory. Systems thinking is instead interested in patterns and processes. It refers not to building blocks, but more to patterns of organization and processes of change that are common to all types of systems on all scales, without interest in reducing higher-level phenomena to those of a lower level. As such, a systems approach is built on a strong emergent view of the world. Given strong emergence, a theory of everything derived from the elementary parts, such as strings, would end up being just one of many components necessary for a complete understanding of the universe, and thus not necessarily the only one. Within the systems paradigm, as all phenomena cannot be simply reduced to an account of elementary parts, the goal of providing a unified description of the world is instead looked for in abstract patterns of organization. Systems thinking looks at how these emergent patterns on different levels have similar dynamics, and from this tries to develop abstract, generic models that are relevant to all scales because they capture the features inherent to emergent processes on all levels. Emergence describes how new, higher-level properties, patterns, and functions form as we put the component parts of a system together. This process of emergence is a pervasive as we put things together. For example, when we look at a flower, we do not see a composition of molecules, cells, tissues, and organs, but in fact we see a whole flower. Likewise, a whole business organization is given characteristics and legal rights that are phenomena in our world, exhibited by virtually all types of complex entities, such as plants, animals, technology, humans, societies, cultures, and economies. It is apparent that new levels of organization are formed as basic component parts, or do they exist in some way independently from the elements that constitute them, which would mean that they cannot be entirely reduced to causal accounts derived from their elementary parts alone. This distinction is not associated with any of its members. Although this emergence of patterns on different levels is apparent, what is not so apparent is whether these emergent organizations are fully determined and understandable with reference to their